Okay, so in the previous video, so that's something I forgot to do, is just to show you what kind of what we were minimizing. We were minimizing the distance between the real observations and this line, this kind of distances. Okay, but you could absolutely that's one way to. So we were trying to minimize the sum of the squares of these distances. All right. But there are many other ways to find the best fit, a nice fit, a nice linear fit for data. Okay, and there are other ways to find the solution of this problem, of this exact same problem. The least square problems. For instance, you know that we are minimizing, so we are minimizing this thing, and we've done enough calculus during semester 1, so that I hope you remember that minimizing this kind of thing, that's two variables, our unknown variables are a and b, and we've done enough calculus so that you know we should take the zero of some Hessian matrix of some gradient, and then try to see them find the minimum. Okay, that must remind you of a few things here. Okay. However, what's happening when we've got a more complex problem? And by more complex, actually, well, what's happening when maybe we don't have a linear, we don't want to find a line, but maybe there's something a bit more complicated than just a line going on. What if you are actually looking for, let's say that's your set, and actually we feel like it should be more like probably an something like y is equal to some polynomial of degree 2, okay, or y is equal y is equal to a0 plus a1x plus a2x2. Okay, that would be, so we still have some observations which are xi, yi, and what's xi and the corresponding, so maybe that's another, that's not the same, I, so xj, y, yj, okay. So this would not per se be a linear regression, because we would be looking for a polynomial of degree 2, or you can think of many other kind of situations where your data appear to be like you've got scattered points and it looks like more or less a circle or an ellipse or something, whatever, and you would like to find the best fit. So that's even another equation. Here you've got something like axi square plus b yi square is equal to some constant. Okay, that would be the equation of an ellipse, for instance. Okay, so you've got a lot of more complicated problems. Another complicated problem is that when your y belongs to R, but actually you've got more than just one xi. You've got maybe, let's give them some name, this is usually called a feature, x1, it depends on some x1 I, on some x2i, of some xni. Maybe you have the product of two of those x1 I times x2i. Maybe you want the square of one of those and x1 I square. Okay, and well, you've got all these datas, and let me give you one example, one very famous and classic example in the field of machine learning. Okay, it's so advanced regression techniques, so we're not there yet. But that's an idea, that's the kind of pedagogical problem, but there's still, you could maybe still find some research going on that kind of things. So what do we have? We have some data that are given. It's a very classical data set. It's the price of houses in the Boston area, and we've got a lot of data related to this price. Okay, so for each house that has been sold, we have a lot of indication. We have its sell price. You see the building class, the zoning classification, the linear feet of the street connected to the property, the lot size in square feet, etc., etc. So we've got, I guess, something like 60 data, 60 different kind of data for each house: number, size of the garage, is that a paved driveway, do we have a pool, do we have a nice pool, etc., etc. So you see, you've got one Y, which is going to be Y is the sell price, and it's going to depend on a lot of features. And maybe again, maybe you have one feature that should be squared, because that's you realize that it's the slope square of the property that is important, and not the slope of the property. Whatever I'm saying, anything. It's just that, okay, you've got the idea is that your Y depends on many, each YI depends on many observations. And the idea is that, well, now that you are given a new house, and you've got all the given data, how big it is, and all these informations, you want to predict its sales price. Okay, and so we're going to do some kind of linear regression on this problem. Okay, we've got this. The idea is that each yi is actually a function that depends on uh, x1i, x2i, x3i, etc. You've got many of those. Maybe the n is not a good choice. Let's take another value, xpi. Okay, but this dependence is linear in the sense that I would get a1 x1i plus a2 x2i plus a3 x3i, etc., plus ap xpi. But you see, it doesn't really it's not a big restriction to us for this to be linear, because I could really say that one of the inputs is actually given by the square of another input. Okay, so that you can, or the cube, or whatever power you think is interesting, or whichever product of two items is interesting. It's things you can calculate on your data. All right, and so this kind of stuff is going to help us do regression. And what's happening, and sorry, I forgot the constant, so it's some a0 constant, and so it's the same idea actually. You are going to look for the projection. The orthogonal projection, of course, because we know that it's the one, the orthogonal projection, to find the minimum of the distance between y and z. Okay, it's the same idea. So you want the minimum, you want to minimize on all the possible a0, a1, etc., up to some ap, whatever the number of features you've got to consider for each data. So you want to minimize this, so it's still a least square stuff, except that this time your z is going to be given by this a0 plus a1 x1 plus a2 x2, etc., plus ap xp. Okay, so basically you're still looking for all these data, right? And so we are doing some projection. We are projecting on, well, the one is going to be used for the a0, and the x1, the x2, the xp. Well, all these are, if I've got, all these belong to Rn. Okay, n, this n here is the number of observations we have. It's the same one as yi I is equal to 1 to n. It's the number of observations. So again, for each I've got n observations, and each of these observations have p features. Okay, so x1, x2 up to xp features, different features that we have to consider, right? And so we're doing the same thing. So in the end, what should we get in the end? We want, it's the same reasoning. We will have that y minus z is orthogonal to each of these. It's orthogonal to 1, y minus z. It's orthogonal to x1, y minus z, orthogonal to x p in the end. Okay? You do these as many times as you want. Okay, so what do you think should be the matrix when you're writing that? Okay, so your homework for the week. So I want that before Wednesday evening, Wednesday, just before midnight. Okay. Your homework is okay. Let's say you've got 4 features. All right. So you've got yi I is equal to 1 to n, and for each yi you've got observation x1, x2, x3, x4. And keep in mind that the idea is that it doesn't restrict you to lines. It's going to be lines for this, but maybe x3 is the product of x1 and x2. Maybe x4 is x2 square. Okay, so it doesn't restrict you to visually align. But what is going? So you want yi to be as close as, well, you want to find a0, a1, a2, a3, a4, x4 to be as close as possible, to give you as close as possible to the y that you are observing. Okay, y belong to Rn, and each of those belong to Rn, right? So I want you to write the same kind of matrix equation we obtained earlier. Okay, here should be the a0, a1, a4. Sorry, we've got only 4 coefficients, a1, a2, a3, a4 here. Okay, what come here? So before Wednesday evening, before Wednesday midnight, I want you to send me via Deposé, as usual, a picture of your matrix equation. Okay, good. Thank you.